I'm Jonathan Briggs, Head of Energy Storage Communications at Argonne National Laboratory. Before we start, please let me explain how we will manage this meeting. For a better experience, please disconnect your VPN. Automated closed captions are available during today's meeting. If you would like to use this feature, click on Live Transcript at the bottom of your screen and choose one of the two viewing options. If you have questions related to the technology of this meeting, for example, if you can't hear or see the presentation, click the chat icon, which is found on the bottom of your screen. Send us a message explaining the issue you're facing, and our AV team will respond and help you troubleshoot. To ask questions during the meeting, use the chat feature at the bottom of your screen. You can submit questions at any time. Some may be answered through a reply in the chat channel, whereas others may be addressed live. Finally, please note we are recording today's meeting and it will be shared afterwards for viewing. By participating in this session, attendees consent to the recording. And now I'm happy to introduce our moderator for today's session, Kris Heckle. Kris is Director of the Materials Manufacturing Innovation Center at Argonne National Laboratory. She is a globally recognized research and development leader who came to Argonne from Corning Incorporated, where she served as Research Director for Inorganic Materials Research and Asia Research Labs. Her experience includes creating a manufacturing platform that opened up new market opportunities for Corning and in energy storage, as well as accelerating product timelines through introduction and adoption of new tools. Take it away, Kris.
Thanks, Jonathan. I hope everybody can see me, hear me okay. Great. So I am very pleased to be on the webinar today, hosting, or rather moderating the discussion. And it looks like my camera is off.
That's correct.
See what I look like. Trying to get it on. There we go. So thanks very much for your patience with that. There's always a little IT. Hopefully I'm the one that got it out of the way and nobody else is going to have an issue this morning. So good morning to everyone, or wherever you happen to be in the world joining in for the webinar. We really appreciate this opportunity to show you how we can support industry for the BIL funding opportunity that's been announced, or the notice of intent has been issued, and you can see the number there, 3098, if you haven't had a chance to look it up. So today we're going to cover some expertise on battery materials processing and the manufacturing grants round 2, and we've got a really great lineup of people to share with you how we can contribute to your work and make you successful as we continue in the transition with batteries in this country. So you can see my email there, and also LinkedIn presence. If you have any questions that aren't answered by any of the speakers, please don't hesitate to reach out to me or anyone else, and I'm committed to making sure that you get the answers that you need. I am the director of the Materials Manufacturing Innovation Center, which is a fairly new position here at Argonne. And I'm essentially a transfer function to link the skills and technologies of the lab to the benefit of the industry, particularly in the materials and chemical processing space. So that's my role and function. And if you'd like to talk about anything battery related, that's today. And if you have other materials that you might like to speak about, that would be something that we could take up offline. So that's a little bit about me. Then what we're going to do today is I'm just going to remind you the various topics that have been highlighted in the NOI. So we're expecting funding in all of these different categories. So I think that when you hear the speakers, you should hear capability and expertise that addresses all of these. So no matter which topic area you're looking for, you ought to be able to find someone at Argonne that can be helpful to you. And if that's not obvious and you're looking at a topic and you're not sure that Argonne's got skills or capability or expertise, please reach out and we will make that connection. So these are the topics that we're expecting to be highlighted when the funding opportunity announcement gets published. So today, here's our agenda. And so this is going to represent quite the breadth of capability that we have at the lab to support you in your application for BIL funding. And first, we're having Qiang Dai, who's going to be talking about modeling capabilities. And I hope that you're going to see a through thread of the combination of experiments and modeling through all of our work. So we don't rely on one or the other, but we believe in the combination of the in physical world and in silico world coming together to solve problems. So we're going to start out with Qiang to really kind of set that point. Next, Kris is going to talk about our material synthesis capabilities that are resident in the Materials Engineering Research Facility, or MRF, as we like to call it. Steve is going to highlight our cell analysis, modeling, and prototyping facility, or CAMP. And then Brian will talk about electrochemical analysis and diagnostics laboratory and post-test facility. And we'll finish it up with, okay, so we've built all these great batteries and they're fantastic, but what happens at end of life when the cycle life goes down and, you know, they're not recharging? Now, what do we do? Jessica is going to talk all about the opportunities that we have in battery recycling. So that's the setup that I have for you. Now I'm going to turn it over to Qiang. So Qiang is a sustainability analyst at Argonne, and she leads our development of the Everbat model, which hopefully you've heard of, and works with colleagues at the Resell Center, like Jessica, to develop economic and environmentally sound recycling processes for batteries. So welcome, Qiang. I'm going to turn it over to you.
For different clean technology, and currently this suite covers batteries, fuel cells, and water electrolyzers, and lightweighting materials for vehicles. So with these tools, we can evaluate different processing technologies. We can benchmark recycled materials against virgin materials. So hopefully with all this information, we can help provide a big picture to all stakeholders and help them evaluate pros and cons of different technologies and plan for recycling infrastructure for all of these clean energy technologies. So this suite of tools are funded by the Department of Energy. As I mentioned, it all started with Everbat, which we first released in 2019 and won an R&D 100 award. And based on the success of Everbat, we started development of the Evergreen suite in 2022. So then maybe a little bit more detailed information about each of the models we have. So for the Everbat model, it focuses on automotive batteries, recycling technologies, and the supply chain. So as you can see, on the chart here, once the battery reaches its end of life, we start with collection, and we can also do disassembly and pre-processing. And after that, we send some of the valuable battery materials to the recycling plant where critical materials are recovered, and then we can use the recovered materials to make new cathode active material, and then after that we can manufacture new batteries. So we developed this model to support the R&D at the Resell Center, but since some people seem to find this model useful, so Everbat has also been used by various stakeholders. And as you can see in this pie chart, we have over 2,000 downloads since 2021, and over half of our users are from industry. And since 2020, we have worked with various industry partners. For example, we have worked with 4 battery recycling prize winners to help them evaluate their logistics solutions for battery recycling. And we will work with one battery recycling company and also support 3 other battery recycling companies funded by the last round of BIL funding. Again, based on our success of the Everbat model, we are developing the Evergreen suite supported by various offices at the DOE. The first one we developed is the Everbat model. This is focusing on recycling of battery energy storage systems. In addition to recycling of batteries, we will also support analysis of recycling of other components of those systems. And also, in addition to lithium-ion batteries, we will be also looking at flow batteries. And we are also supported by the Hydrogen and Fuel Cell Technologies Office to develop this Ever Hydrogen Tech model to evaluate recycling processes and supply chain of electrolyzers and fuel cells. Lastly, we are supported by the Vehicle Technologies Office to develop a model to help evaluate recycling processes for different aluminum alloys for vehicle lightweighting. So what can we do with the Evergreen suite? So I'm going to show you some examples. Those are examples from Everbat, but they will apply to the other three recycling tools as well. As you can see, with those models, we can evaluate cost and environmental impacts, including energy consumption, water consumption, and criteria air pollutants, including SOx, NOx, and greenhouse gas emissions. So we can compare different recycling technologies at the process level. And we can also compare different technologies at the product level and also benchmark recycled materials against virgin materials. With those recycling models, we can also take a look at all of these stages along the recycling supply chain and identify hotspots. For example, here we're looking at the cost and revenue we can get from each stage along the battery recycling value chain and identify the big contributors and opportunities for improvement. That's what we can do regarding different recycling technologies, but we are also looking at how we can support processes development beyond recycling. That's why we are also developing the impact model, which stands for Innovative Manufacturing and Processing Assessment Calculating Tool. That's a mouthful. So this tool is an Excel-based model that, again, can help evaluate the cost and environmental impacts of advanced material manufacturing and processing technologies. So for this model, we will leverage the capabilities Argonne has at MERV. So Kris will give a presentation about the facility, but spoiler alert, they have had vast experience with development of novel manufacturing technologies and also scaling up those technologies. So we propose to leverage their experience to develop the model focusing on novel manufacturing processes and how we can evaluate the performance of these processes as they scale up. currently, we already have plans to work with 3 companies funded by the last round of BIL funding to evaluate advanced manufacturing technologies for battery materials. And we will also use this model to support the Hydrogen Fuel Cell Technologies Office to help them evaluate technologies for fuel cells and electrolyzers. So again, a few examples of what we can do with the impact model. First, we can support analysis for process scale up. For example, we can evaluate how the manufacturing cost is going to change as we increase the manufacturing capacity, and each of the point here represents one analysis scenario we conducted, and for each scenario we can also take a closer look at the major contributors to the cost and the cost breakdown. Another example I can share is we can use the model to support process optimization. One easy parameter to use as an example is the process yield. With the model, we can analyze how the cost is going to change if we can increase the process yield, or what an improvement of process yield can do to help reduce greenhouse gas emissions. And we can also figure out the break-even point of the process we are analyzing compared with, for example, commercialized technologies for a specific material. That's all I have shared for today, and thank you so much for your attention, and I will be happy to take any questions.
Thank you so much, Qiang. That was a really great overview of the capabilities that you've developed. I am getting a little bit of, yeah, of course, you're welcome. I am getting a little bit of interest in how do you collect the data that allows you to validate these kind of models?
That's a great question. So for cost, well, I guess the short answer is it's difficult to validate results from our models. For cost, it's not easy to get industry to open their books to you and tell you exactly how much it costs to produce a product. But we were able to validate our results from the Everbat model based on, for example, how much recyclers typically charge or pay to get black mass or end-of-life batteries, or assuming that they are going to operate to recoup what they pay. And our results mostly confirm what we have learned from the industry. So I would think our models are relatively, well, not necessarily accurate, but reasonable.
Yeah, within the ballpark, perhaps.
Yes.
Thank you. So I hear you say that you're doing the best that you can to validate the models with data that can be made available to you. But if there were companies who wanted to provide some, let's say, test data or ideal case data, even that would be useful to you.
Yes, of course. And also, I would like to mention that in our models, we actually have a lot of parameters and factors considered. So depending on the level of detail the company is willing to share with us, of course, the more data we can have, the more accurate the results will be. Yes,
exactly. Okay, and then there's also some interest in the impact model. Can it tell you much about geographical or regional specificity?
Yes. So one thing I forgot to mention is that for the impact model, we focus on the US, but we are able to differentiate between different states. So we are able to consider, for example, differences in labor cost or electricity mix in different states.
Great. Thank you so much, Qiang. I really appreciate that.
Thank you so much, Kris.
Yeah. We are going to continue on with our program to give everybody else some time to speak. And so for everybody that's just recently joined, this is the agenda that we're embarking on today. And so we finished with the modeling capabilities that Qiang has just reviewed for us. And please remember to leverage the Q&A or the chat for any questions that you might like to ask. And you can ask any panelist at any time about their content. So you don't have to worry about it's too late to ask Qiang a question. Of course, that's not true. So at this moment, I'd like to introduce Kris Pupek, and he is the leader of our materials engineering research facility. And after a more than 20-year career in industry and pharma and chemicals and other aspects of processing, so he leads this facility with a sensitivity to what industry is going through. And so I think that you'll find that his expertise and commentary are really relevant to the topics that we have today. And now I'll turn it over to Kris.
Hey, good morning, everybody. I'm glad to, let me see, I can share my screen. Okay, one more click. Okay, can you see my screen in the presentation?
Yes, thank you so much. Yep.
Okay, great. So once again, good morning, everybody. I'm glad to introduce you to Argonne's Materials Engineering Research Facility that I have a privilege to lead. And that's a little bit formal information, what the facility came from, a little bit history. So it was established in 2009 and remodel and expand, basically double the space in 2019. So the history is not that long compared to Argonne. It's about 28,000 square foot of labs, mostly, a little bit offices, a little bit chat rooms, but mostly the labs. Currently, there is over 40 scientists, engineers, and supporting staff working in the facility. So, what are we doing, and what's actually the purpose? The main objective is basically bring the advanced manufacturing technology to domestic industry. The new materials, especially materials for energy, electrochemical energy storage, are discovered in the labs frequently, but the way from the discovery lab to the manufacturing is very long and very bumpy. So we basically try to help the discovery scientists turn the discovery into the commercial product. We basically want to shorten the time from discovery to commercialization. We develop the processes for making this material in the larger scale. We basically prove that the material that was created in the small amount in the discovery lab can be made in the larger scale in the way that can be acceptable by industry and without losing the property and performance. As a proof of point, we actually make kilograms of the materials. Obviously, depend on the material, and we submit the samples for prototyping, evaluation, and to support the further research. The benefits of the group I'm leading is that most of the core staff has a long industrial experience, which is very, very important. The scale up and process R&D are typically not taught on the universities. This is the kind of skills and knowledge that you can get only working in the field. And I am privileged to work with the people who already have those skills. So, and the other thing is that we basically work on the two tracks. We use the standard process R&D technology to make the kilograms of this material. On the other hand, we evaluate this new emerging technology, how to make this material more efficient way. Some of those advanced material cannot be or would be extremely difficult to make using these traditional methods. That's why we heavily investigate in modern technology method. We use data collection in situ and operando data collection during the process that give us insight into the chemistry and physics of the process that help us to basically design a better way how to make this material more efficient way. I believe you saw the picture from the slide from the previous presentation, but I want to emphasize one more time that this is basically the modern technology we try to apply for process intensification and make this new advanced material more efficient way. Those are continuous flow processes. There is a flame spray and reactive spray pyrolysis that I will talk a little bit more. Taylor vortex reactor, hydrothermal processes, and so on. We have a very broad portfolio of project that covers all possible materials for electrochemical energy storage. This is not only cathode, which is the most common material people talk about, but this is anodes, this is electrolytes, this is binders for advanced electrodes, and other materials that are needed to put together so complex system like working electrochemical cells. The best examples how I can describe our capabilities will be by showing a few projects and describe the project. On the left of the slide, you see that we have a continuous stirring tank reactors, which is basically standard for co-precipitation of the precursor for cathode material. But we do have advanced systems, actually cascades of these CSTRs to make, for example, gradient materials. But we went one step further. We want to evaluate if other co-precipitation technologies can be used for more efficient and rapid process development. One of the technology we explore is a Taylor vortex reactor. On the left bottom, this is type tube-in-tube reactors, which is a horizontal. A lot of benefits that we prove in the past 5 years or 6 years that can produce much better material, save on energy, save on time, save on materials. The other in the middle of the slide is the hydrothermal processing. Hydrothermal processing are the chemistry that is run in supercritical fluid. As you know, supercritical fluids has a completely different properties than fluids in the standard condition. We have two systems. One is the batch supercritical reactor, and the recent addition is actually continuous flow supercritical system. All materials that need to be produced in the high volume need to be run in the continuous process. Otherwise, the economy will not be there. So why we are using this? As you know, the cathode material that can be made through co-precipitation process, like in these two instruments on the left, so-called polycrystalline materials, and there is a lot of problems. The degradation, physical degradation of this polycrystallines cathode material is one of the main reasons why the battery basically fail after the time. There is a lot of interest currently in the single crystal cathode material. In the single crystal cathode material can be made in a few ways, but the most efficient way is to run the process in the supercritical fluid. Our reactor is a supercritical water, operates at 380 degrees C and 230 bar pressure. So you can see it's a extreme condition that are needed to take water into the supercritical state. On the right, there's yet another technology. It's a flame spray pyrolysis and reactive spray pyrolysis. Those are similar but quite different technologies. This is the technology that we didn't develop. This is a known technology. A lot of commodity materials like carbon black or fumed silica or titania is made in this technology. We basically adopt this technology and tweak it to make very complex material like solid state electrolyte, LLZO, for example. We make the nanomaterials that is used to coat traditional NMC cathode material, and it's an extreme complexity of the process for flame spray pyrolysis. To better understand, we put a lot of inline instrumentation. We have a laser PLEF for flame diagnosis. We have optical sensors. We have inline Raman spectroscopy. We have an inline particle size analyzer, and the data amount we collect from all those instruments is enormous. It's beyond what human being can process. So we set up with our friends from computer department, set up the line. The data in the real time is being to the supercomputer, and we use artificial intelligence algorithm to try to figure out what is the relationship between all the parameters. We can set the process and the properties of the materials we produce. The hope is that over time we will better understand all this relationship, and then we can basically tune the process parameters to achieve the desired property of the materials.
About 3 minutes left, Kris. Thank you.
Oh, sorry, I talked too much. I'm sorry. So yet another, I will try to do quick, another set of projects we have is for electrolytes, new cathode material, new anode material. They require new liquid electrolytes, and we have a dedicated continuous flow laboratory when we use autonomous discovery technology, which is the picture of the system is on the right bottom, is basically component of 3 elements: continuous flow reactor with inline analytical tools and machine learning module to rapidly develop process parameters for those materials. As I mentioned, our portfolio of materials for electrochemical energy storage is very broad. This is a slide that show you our work on actually polymers for for energy storage. We work on the conductive, electron conductive binders for silicon anode, the so-called self-healing polymers for silicon anode, modification of binder and so on. So we are working with other national laboratory, which is obvious, with academia, but most of our collaborators are actually came from the industry. As I said on the beginning, our main goal is to help domestic industry to basically advance their technology and accommodate the new technologies. We are open to discussion, ideas, collaborations. If you have a question or you have some idea how we can help you, we will be glad to discuss. My contact information is on this slide, and at this point, I will pass the torch back to Kris.
Thanks, Kris. Yeah, and I can definitely attest to Kris's expertise and willingness to work with industry. So please don't hesitate to reach out. In fact, one of the questions that we received was how, do you work a lot with industry? And then you answered that with that final slide. So that was very prescient on your part. Thank you much for your talk. And for the interest of time, we're going to, we do have a question in the chat, so I'll let you answer that online.
Absolutely.
So we're going to move on to Steve Trask, Steve is a senior engineering specialist at Argonne, joined camp in 2011. And he has expertise in making slurries and fabricating prototypes and figuring out all the problems that go on with making slurries and fabricating prototypes, investigates and mitigates problems, all of that stuff. And so optimizes electrode formulations and cell fabrication techniques, and a very expert, and we're really pleased to have him here today. Turning it over to you. Thank you.
Thank you, Kris, for the introduction. Yes, so again, my name is Steve Trask. Been working at the camp facility since 2011, and I've enjoyed being able to work on the development for slurries and electrodes for the project. So what the facility does is focus on wanting to transition experimental battery materials from benchtop science to industrial production through independent validation and analysis. And we do this with testing then in prototype cells. We use semi-automated equipment. So it's a not fully automated process, but we work with making special electrode coatings and cell builds that have high quality. And we perform all this work in a dry room, and it can have up to 8 people working in there, maintaining a dew point of around negative 47 degrees, 43 degrees Celsius. And the team has expertise in materials validation, and then we utilize modeling and diagnostics. In terms of the utility in the facility, there's electrode design that is critical to get high quality electrodes that are industrially relevant. And we do this with roll-to-roll coating. We have a calendaring unit in our dry room decrease the porosity of the electrodes, and then the electrodes are then demonstrated in 2 different format sizes that we have in our facility currently. And the capacities can range from 20 milliamp hour up to 3 amp hour, depending on which format we choose. And then we perform the electrochemical testing and data analysis on these cells. This is a team that is coordinated with several different Argonne facilities, the EADL facility, RECELL facility, and the MRF facility that Kris just spoke about, and the post-test facility for post-mortem evaluation. In terms of the history of the camp facility, started in 2010, and in 2018 we had a large upgrade in terms of our size of our dry room. So it's 3 times the size that it originally was. And in terms of newer equipment, we just had a multifunctional coder installed, which I'll talk more about in the coming slide. In terms of the approach, like I mentioned, we want to validate and demonstrate promising chemistries in a larger format cells. And so in order to do that, we need to rely on researchers and collaborators such as MRF or other organizations to provide the materials, since we don't do the synthesis in-house. And then we'll take them through the process of the slurry development and coat them into electrodes. And that can then be used to demonstrate the merits of the promising material. The great thing about this facility is that it can work with early stage scaling up. So we can work with materials that are provided from 10 grams up to 2 kilograms. And often there's a challenge with initial scale up that might take a lot of work just to make 50 grams of say a cathode active material, and we can work with that quantity and make high quality electrodes that are also designed to be have a proper matching for a corresponding electrode, and then get several meters out of even that small amount of material. So in the pictures, you can see we start from a powder, it gets turned into electrodes, and then from there it can go into different format sizes. Sometimes we do specialty cells where we have reference electrodes placed in the cell, and then they can also be turned into multi-layer cells. So an example of some cells on one of our test pictures. And then moving on to doing electrochemical testing to check on how the performance is. And we are roughly at 100 times the capacity of a coin cell, and 100 times less than what's in the PHEEV. So we kind of call our camp zone around 400 milliamp hour. But like I mentioned earlier, depending on what the project is and what the needs are, roughly 20 milliamp hours up to 3 amp hours is what we're capable of. So inside our facility, we have quite a few different types of mixing equipment. Also in the dry room, we do have our 2 coders as well. And these different mixing equipment enables us to work with small quantities to up to 2 liters in size, and also the mechanisms in which the slurries are made. There might be some requirements in terms of how it needs to get blended. For example, CMC SBR need to have more of like a mixing and kneading type of mix, where you want like a dough, compared to typical PVDF NMP. So we have all these capabilities in our facility. For our two coders, the image of the coder on the slide is our original coder. So this is a reverse comma coder. Works really well with coding smaller slurries and being able to control what the loadings are that we are targeting. And the newer coder, which will be images will be on the next slide, show how we can coat with slot die. We can coat with gravure coating heads, and there's other features too on that newer coder. And they both have two drying zones. The newer one actually has an extra drying zone as part of it as well. And there's a heated roll press for the calendaring, and then the semi-automated cell assembly equipment's also located in the dry room, where we do the welding and stacking of the electrodes and sealing and filling the cells. So this is our new multifunctional coder, and this has some really unique features. It has most notably, has an interchangeable coating head system. So these are modules that they're mobile, so they can slide in, slide out. Currently, we have slot die and gravure, and then more can be ordered as needed, depending on what the projects are that we're part of. And this unit also has a corona treatment for treating the foils, improving the adhesion. The IR zone in the oven for coating a very thick electrode, and then might be tending to slump on the edges. The IR system can assist with that. In terms of how the camp facility is supporting the battery community, specifically for VTO projects, we have something we call the electrode library. So it's a library of electrodes, anodes, and cathodes that are all capacity matched. And currently we have 12 anodes and 15 cathodes in this library. We've sent these electrodes to national labs, and universities, and industry partners for collaborations that we're part of with them. And the library, the anodes, are 2 millibars per centimeter squared, so somewhat on the lower side in terms of capacity, but it can be really useful just to do initial studies, testing out, say, an electrolyte, or if our collaborator is wanting to, they're mainly focusing, let's say, on the anode, we can provide the cathode to them, and they don't have to worry about making their own cathodes for that. And then we also make higher loading electrodes as well, up to around 6 millibars per centimeter squared. But those aren't part of our library, more specific to the projects we're part of. And then after the electrodes are made, they can be punched into different dimensions to either make single layer pouch cells or multi-layer pouch cells. And so the different format sizes yield different cell capacities. Here's an example of some of the projects that we're part of. It's quite a vast range, and what makes it fun is that there's a lot of different materials that I get to work with in terms of developing well-dispersed slurries and high quality coatings. So there's a list of some of those materials on the right side of the screen, and also additional experience that we have is working with solid polymer electrolytes, and then working with the APS, which leads me to this slide. The next three are just some examples of some studies that we've done. So this is us leveraging some of the capabilities at Argonne, working with the advanced photon source, and it gives us a chance to investigate internal bulk microstructure and interfaces for the solid state electrolytes. And so we provided a pouch cell to have it examined at the APS, and they produced some pretty fancy images like this.
Steve, about 3 minutes left, please.
Okay. And another project we're a part of is the fast charge program. And so this slide is highlighting how we, the baseline R1, that's a lower loading cell. So around 1.5, 1.6 millibars per centimeter squared. And it's able to handle the fast charging quite well. And then when we bumped up the aerial capacity, keeping all the parameters the same, we couldn't get as much utilization during that first charge or during that fast charge. And then so we made modifications, changing the carbon binder domain. Then we were adding, switching up the separator that we're using, and then using advanced electrolytes that were enabling it to get better utilization. So we're able to kind of factor in all these things at the camp facility and know exactly what's going inside the cell, and to be able to understand the impact on the performance. On the right side, there's our work with doing dual layer electrodes. So in this case, we're doing larger particles on the bottom for the anode, and smaller particle sizes on the top. And this is what modeling it suggested, and it proved to be working quite well. This last example here of some work we've done is on the silicon side of things. So one of the things that we've seen is just the challenge with going higher loading electrodes with silicon, and some of the adverse effects when we go higher loading is some of the stresses that are put on the electrode itself. And so you can see some of the stresses when we went to the from 1.3 to 2.2 millibars per centimeter squared when we had just the silicon in there. And then on the right side, we blended some graphite in there, but we're able to increase the aerial capacity, but we still have the ring clean. And so we've sent many electrodes and cells and data to many of our partners, and here's some examples of universities, the industry partners and national labs that we've sent this to.
Great, Steve. Thank you so much. Yeah, as people look at your final slide, there is an interest in the chat, if you don't mind typing it in rather than answering it live, about how can people come into camp and use the facility, or do you provide the expertise and the technician support, or can people use the equipment directly? So if you'll answer that into the chat. And also, Kris Pupek, there's a question for you there too, if you could take a look, please, because we're going to keep moving, and we're going to turn it over to Brian Ingram, who is a material scientist and group leader of electrochemical analysis and diagnostic laboratory and post-test. And so as you can imagine, Brian and his team study how the batteries are behaving during cycling, and then after cycling, they study what happened to the material during the life. And he also is a co-director of C Steel, working on blast furnaces for next generation of steel making. So thank you, and I'll turn it back to Brian.
Okay, thank you. Is the screen sharing it correctly?
Yes, everything is good. You sound perfect.
Thank you, Kris. Yeah, so yes, I'll be talking about sort of as we continue the progression through the energy storage process here of scale up and development of components and cells themselves. Here we are looking at our capabilities of testing and evaluating cells, and then also doing the post-operation or post-test analysis of the cells. So the Electrochemical Analysis and Diagnostics Laboratory was established as a versatile battery testing laboratory with both software and hardware that accommodates a wide range of profiles and protocols, as well as cell sizes, as I'll be discussing. We provide technical support and evaluation for both the DOE as well as the US ABC and other industrial partners. We can evaluate performance, calendar life, and have also developed some life modeling and projection software, which I'll be discussing. We do provide an independent agnostic evaluation, or elevation as I wrote, of emerging energy storage technologies. We were established originally in the late or mid 70s, just about my time era at least, and have evolved through a lot of the energy storage technologies that have been developed over the last 40 plus years, as well as the fuel cell communities. We can look at a wide range of chemistries and technologies within that space, and anything that's really commercial or technically relevant is something that we support. So the facility has a wide range of capabilities. We have physical capabilities, test stations. We have about 240 test stations that span a wide range of voltage and current capabilities. So we can test anything from single layer pouch cells all the way up to battery packs. We tend to, especially in the recent testing and evaluation space for EV applications, tend to focus a lot on single to tens of amp hour multi-layer pouch cells is where we do a lot of our current efforts. We certainly will match our test channels to the specificity of the system that needs to be tested to meet the specific load demands. All of our hardware test stations are coupled with environmental chambers to maintain tight control of temperatures during testings. Our testing temperatures can range from anywhere from 100 degrees Celsius to well below 0 degrees Celsius. We also have a wide range of expertise in the group and in the facility, having seen many different technologies being developed over the last several decades. So we can offer consultation and test planning, data analysis, as well as performance evaluation. We've tested a wide range of chemistries in energy storage, from your current EV predominant chemistries such as lithium ion coupled with NMC materials. We've also looked at lead acid batteries, zinc air batteries, and sodium sulfur batteries, to name a few. We have looked at many different systems and scales of systems across the TRL levels, spanning from fairly low TRLs up to fairly high TRLs. And you can see some examples of the scales that we have tested and evaluated over the recent years. So one of the strong benefits of the EADL is that we have our tests are controlled with custom software that allows for control of the test itself as well as data acquisition. We are able to collect data simultaneously, temperature, power, voltage, etc., at high rates. We're also able to do, as you'll see on the next couple of slides, custom testing profiles that meets the needs of the technology or application being evaluated. All systems all test stands, I should say, are operated on individual computer nodes. So they are isolated from all other testing at the facility, which helps to maintain one, robustness of the tests themselves, as well as isolation for any proprietary information that would be collected. As I mentioned in the previous slide, the battery life and performance testing is guided typically by established protocols for existing technologies such as EVs or PHEVs in recent years, but is also highly customizable. All plans will follow a general approach, which is to establish a baseline and performance of a target or targets of measurable metrics, capacity, resistance, and energy, deliverable energy, for example. We can age the battery under defined conditions if you're doing, for instance, cycling life or calendar life. And you can see on the right an example of what is a current USABC standard dynamic testing cycle for EV application. We would repeat that performance test at established intervals, and these would be considered your HPPC testing, typically every 100 cycles or every 32 calendar days. Certainly, this is defined as appropriate for the target application. So, for example, in fast charge applications, we typically will address the number of cycles because the fast charge, you of course get more cycles in a given time. We track the changes in performance of cycle or time, and here you can see on the right and the bottom a very typical or example schematic of the energy power ratio relationship as a function of this interval time, moving from right to left, comparing it to the energy goals of the target application. Effects of stress factors, temperature, power, state of charge, etc., can be isolated individually or in combination. And we evaluate and continue this process until the end of life targets are reached, which are typically defined in standard protocols, like, for example, the USABC manuals for EV testing. But also we do this in agreement with the program or project managers or the individual industry or developers that we work with. In terms of establishing calendar life, which is a very important topic from many energy storage systems, we developed an analysis tools and software to evaluate or predict the life capability with minimal testing requirements. And we can support applications that target 15 plus years of life in a relatively short 1 to 2 years worth of data or less. This battery life estimation and data analysis, or BLE software package, functions on a data fitting, and this is an example equation, not to get into the details, but this is a fairly typical data fitting equation we would use that uses both time and temperature data points and fits this Arrhenius model with the existing data. It provides an error estimation within that fit, as well as a Monte Carlo simulation that outputs a probabilistic life estimate with upper and lower confidence interval limits. And so here you can see sort of a schematic, on the x-axis would be time, and on the right, the vertical axis would be the sort of the probabilistic evaluation of the counts in the Monte Carlo simulation. It would be associated with the amount of time predictions. This software is available for licensing at no cost for DOE and USAB contractors. There is a nominal fee requested for general users. So upon the testing facility and evaluation, we also provide the availability of a post-test analysis facility. It's a combination of a wide range of microscopy, spectroscopy, and chromatography, tools, techniques that are integrated within not intern atmosphere, but a inert atmosphere. So we can establish the fundamental degradation and failure mechanisms associated with tested cells or modules or even packs. This is an analysis at the materials, interface, and component level. It provides independent assessment of materials level mechanisms, and it mitigates the effects of any error exposure during this evaluation. So if there's error effects or degrades, for instance, electrolytic compositions, we can mitigate that effect. And we probe, as I said, the solid materials, the liquid electrolytes, as well as the interfaces between. This facility was established in around 2010 to couple the physical mechanisms to observe electrochemical behavior. Here's a list of the wide range of interactive techniques that we have available. These are all integrated into an inner atmosphere, except for the NMR and the SEM. We do have for the SEM a transfer system, however, that does allow for the samples to be delivered to the SEM under inert atmosphere. One unique aspect of our expertise provided at the post-test facility is not just the operation and development of technical results, but rather also combining techniques in a research environment that allows new approaches. And one such example is electrospray ionization approach. And very high level, we're able to inject extracted electrolyte or fresh electrolyte into our GC system and evaluate at multiple different injection temperatures. Coupling that with our FTIR and Raman, we can look at the available species and underlying coordination of those species. By doing this at multiple input temperatures, we're able to use Arrhenius models to extract the thermodynamics of desolvation for individualized species, and then look at that information as a function of, for instance, the concentration of the species or of the electrolyte. And so with this type of combined approach and expansion of the individual techniques, we were able to provide direct measure of the desolvation of lithium ion solvation species in various different electrolytes utilized across different development technologies. And so in this case, electrolytes with lower desolvation energies were found to improve the fast charging capabilities of a series of different systems that were under investigation. So the use of the post-test facility is not just for post-test analysis, but rather it can couple into many of the various different research and R&D efforts across DOE, for instance. So Steve mentioned in this previous talk, many different VTO consortiums that we support, as well as any R&D or interest level from an industry partner that we would work with. So I want to thank you for your time. My contact information was on the front side of this, which will be shared at a later date. And these are the individuals that are involved with these two facilities.
Thank you, Brian. You know, I had the IT issue earlier in the session, and you have the typo, so that's not so bad. We can
I know,
split the responsibility.
yeah. Sorry, everybody.
Yeah, no worries. So
I'm a scientist, not an English major.
Right. The question that we are receiving is we've talked a lot about, looks like lithium ion. Can you talk about some of the other battery chemistries that these facilities might be useful for?
Sure. So currently, the vast majority, if not the entirety of our research and evaluation portfolio is in the EV space, which does align with lithium ion. We have had, as recently as a few years ago, we were looking at sodium ion systems and various other chemistries, as I mentioned on the one slide. We are currently exploring opportunities to expand to some of the more priority research directions and development directions. They're in like the BIL space, so long duration, lead acid, flow batteries, etc. So we are quite versatile and interested in supporting technologies and applications beyond the EV lithium ion space.
Yeah, great. Thank you so much. I appreciate that. And then if other people have comments or questions they'd like, please go ahead and leverage the chat. But we are going to move on to Jessica, who's going to be covering the battery recycling effort. And so Jessica is a principal materials scientist in materials recycling R&D group here at Argonne, and she's a lead investigator on the Resell Center. She works on safe and cost-effective recycling processes for lithium-ion batteries, and is the focus area lead for direct recycling of materials, including like cathode active ready. So we're going to turn it over to Jessica to bring us home and talk about what we do with all these excellent batteries once they're used up.
All right. Thank you, Kris. I'm hoping you can hear me and see my screen.
Yes, it's perfect. Thank you.
All right, great. So good morning, everyone. Last but not least, I'll be talking about recycling and what has to happen to end of life batteries. So first, I'll kind of give you a brief overview of what we're doing here at Argonne and battery recycling. I don't want to spend too much time on this slide because this information is covered in the presentation, but I'll just hit a few points. We have facilities, capabilities, and expertise in lithium-ion battery recycling. As you saw earlier in Qiang's presentation, we have the EverBat model, which helps us to assess the economic and environmental impact of battery recycling processes. We lead a center called the Resell Center here, which was established in 2019. Through that, we work closely with national labs, industry, and academia to address battery recycling opportunities. It's really important for us to be working with industry, so that's a big part of what I'll be talking to you about today. Hopefully you can't hear the building announcements in the background. But we do bench scale and proof of concept testing, also process optimization and scale up. Most of our projects here are funded by the Vehicle Technologies Office, and also some by the Advanced Materials and Manufacturing Office in DOE. And first, I just briefly want to talk about why should we recycle batteries? So first, we want to keep more solid waste and batteries out of the landfill. We also want to reduce the reliance on foreign countries. So batteries contain a variety of what are called critical materials that can include lithium, cobalt, nickel, and graphite. And these materials we don't have very significant reserves of, so we source them from other countries. In addition, we reduce our environmental impact. A lot of these materials I mentioned are mined or extracted from geothermal brines. So by taking materials out of batteries and reusing them, we can reduce the amount of mining and extraction of materials, thereby reducing environmental impact. One other thing I want to point out is when you're thinking of battery recycling, the reason why this is becoming more and more important is because we're talking about electric vehicles. Electric vehicles have large batteries that contain a lot of material, and there are over 1 million electric vehicles on the road today. However, these EVs won't reach their end of life for another 10 or 15 years. And also, if you think about 10 or 15 years ago, there weren't very many people driving electric vehicles. So while we're waiting for the batteries in electric vehicles to reach their end of life, we need to start thinking about where else we can get materials for recycling. One very promising place of material is electronics devices. This is e-waste or consumer electronics. There are currently over 100 million cell phones that are being thrown away in the landfill every year. And if you're anything like my household, you might have cell phones, old laptops and things like that just sitting in the desk drawers in your house. So right now, these aren't a huge source of material, but can be if the collection is improved for getting these materials to recyclers. One other area is manufacturing scrap. So in the meantime, it's expected that the battery recycling industry will be relying on manufacturing scrap as an input, and expected that 80% of the material for recycling will come from manufacturing scrap within the next couple of years. And I mentioned earlier that Argonne leads what's called the Resell Center for Advanced Battery Recycling. Here at Argonne, that allows us to bring together battery development, process optimization, scale up, recycling, and modeling in one location. We've led the Resell Center since 2019, which, as I mentioned, is a collaboration of national labs, academia, and input from industry. I also want to mention that we have the materials recycling R&D group here at Argonne, which Resell is part of. And in that group, we also work on recycling other materials. So these include critical materials, plastics, and electronic waste, various metal streams, and things like that. And through all of our work, we work closely with industry, and our goal is really to help industry succeed in the recycling space. The Resell Center, as you can see here, is a collaboration. We're really trying to bring together battery recycling expertise to help bridge the gaps that are keeping the US from realizing the most successful battery recycling infrastructure. And with this group, we work to develop cost-effective and flexible processing technologies to extract as much profit as possible from current and future battery recycling technologies. And to that end, we are working to develop technologies in all areas of battery recycling as a way to decrease costs and increase profit. This is important because nobody's going to want to pay to recycle their old batteries. So we have projects working on pyrometallurgical processing, which is high temperature recycling, hydrometallurgical processing, which is solvent-based, leaching materials into acid, getting those back out, and then what's called direct recycling. So through the pyro and hydro processes, you're breaking down battery materials and then having to remake them into something that goes into the battery supply chain. But with direct recycling, we really are able to minimize the steps back to use because we're targeting especially the cathode material, which has a lot of those valuable metals, getting it out of the battery without breaking its structure down. So basically, we take the cathode material out, we clean it up and regenerate it and put it back into a battery again. You can see this circle is much smaller. And this is where almost half of our work in the Resell Center focuses on. This is a newer area of recycling, and there are a lot of challenges to solve. So if we look closer at direct recycling, there are many steps involved in breaking apart the battery. and separating and getting the materials back out, especially so you can target things like cathode materials to put back into batteries, but also so we can separate out the other streams of material to help increase profit in a recycling pathway. At Argonne, we have capabilities to do every step of the direct recycling process. We shred batteries, we recover the electrolyte and put it back into batteries. We're able to separate the different materials. So the cathode material, which is typically a metal oxide, the anode material, which is graphite, and the different metals you would find in a battery cell. We have different technologies we've developed to remove the binder from the cathode and anode electrodes, so we can get back a powder material to send to our recycling processes. And then also generated various technologies to relithiate and upcycle cathode materials to put them back into batteries. And going more into our facilities, I just want to be able to show you some of the capabilities we have. We currently occupy 3,000 square feet of high bay space. We have bench and pilot scale labs, which are co-located with the MRF, the Materials Engineering Research Facility that Kris Pupek talked about earlier. We have a variety of equipment. This is a short list, and I've selected a few pictures. We have lots more capabilities that are not listed here. So if there's something you're interested in, please reach out to us so we can further figure out what capabilities we have that can help you. But as you can see here, this is a custom built inert atmosphere shredder we have. We're doing froth flotation for material separation, especially to get back anode and cathode powders, optical sorters where we can sort materials based on their color, shape, and size, and a large rotary kiln, which we do various heat treatment methods such as thermal binder removal and relithiation. As I mentioned, we don't only recycle battery materials, but we can recycle and separate all the materials in batteries. So this includes the plastics and other metals you may find. We have additional capabilities I'm showing here, wet separation systems to allow us to concentrate metals and separate different types of plastics, as well as other types of separations, which allow us to concentrate ferrous metals, non-ferrous metals, and allow us to separate and concentrate light materials. So as an example, and in this area, I wanted to show you that we work with companies heavily in this area. We recently worked on one of Argonne's lab to market funding opportunities where we process e-waste material from 2 companies, and we process at industrially relevant scales. So we were processing 10 to 15 tons of material for each of these companies. And you can see we get materials in a Gaylord bin. This is about 1,500 pounds of material that we're processing through our systems here. So we really do large scale and industrially relevant processes. And that brings me back to battery recycling. I've showed you some of the equipment we have and some of the capabilities, but right now we're actually renovating 12,000 square feet of high bay space here at Argonne, which will house our direct recycling pilot plant. And this pilot scale space will have equipment that allows us to handle at least 10 kilograms of battery materials a day, which translates to about 2.5 tons a year. And this is important for resale. We have over 20 patent applications and 50 publications related to lithium-ion battery recycling. And our main goal is to expedite the transfer of new technologies to industry. The unit operations you see here were developed at the bench or small scale. And the pictures shown have our pilot scale equipment that we've purchased for our pilot plant and we've gotten up and running. but we really need that new space to house the rest of the pilot scale equipment we're purchasing. By getting these technologies to industry faster, we'll be able to handle those batteries that will be coming back from vehicles in the next 10 or so years. I also want to point out that all of the capabilities I've shown you today and the capabilities that will be in this pilot plant area that I mentioned to you will allow us to have a flexible research space, and the unit operations can also be used for other types of projects, such as critical materials R&D and other similar research areas. And I just want to wrap up the presentation by saying that feedback from industry is very important for us. So what we do through RESEL is host an industry collaboration meeting. We did this in November of 2019, and then we were just able to host it again this year after COVID. So we have a meeting so we can get feedback from stakeholders in all areas of the battery value chain. And I just want to point out that there will be another meeting in the spring of 2024. So please keep an eye on our website, reselcenter.org. That's where we have a list of events that are happening. So keep an eye out. And also you can sign up for a newsletter so we can let you know when these events are coming up. But thank you for your time today, and feel free to contact me if you have any questions.
Perfect, Jessica. Thank you so much. Really appreciate it. So thanks, everybody. This is at the end of the webinar, which is our final webinar. We've had a couple of others. So a few people in the chat have asked, will the slides be available? And yes, we are going to send out the recording and the slides. These were the topics that we covered today. So we have expertise in all these areas, and we really want to support you as you pursue BIL funding. There was one question in the chat that remains unanswered, I think, and that is who's designing batteries to be particularly recyclable? And we have 1 minute left. Does anyone want to take a stab at answering the question of how are we approaching the topic of designing batteries specifically to be recycled?
Hi, Kris. Yeah, we do in RESEL have a focus area dedicated to what's called design for sustainability, where we're looking at how do we make batteries easier to disassemble and recycle, in addition to some other types of research. So again, if you go to reselcenter.org, we have a space on our website that explains what we're doing in that focus area.
Perfect, Jessica. Thank you so much. So thank you, everyone, for attending, your interest, your participation, and we look forward to hearing from you, any of us at any time. Thanks very much. Have a great day.